Okay, measuring Brinell hardness. In concept, measuring Brinell hardness is pretty simple. What you do is you take a round ball and you press it into a surface, and that deforms the surface. It makes a little pocket, a bowl-shaped pocket. And if we know the force that's applied, this is measured in kilograms force. If we know the diameter of the ball, we can measure the diameter of the resulting dent. And basically what the Brinell hardness is just the pressure on this surface area. So knowing the diameter of the ball and the diameter of the dent, we can calculate the surface area of contact with the ball. So if we take the applied force and divide it by that surface area, we get a pressure, and that pressure is the Brinell hardness. You can use any size diameter ball you want to and any magnitude force, but you'll get different results for different magnitudes of force and different diameter. So the applied force and diameter of the ball have been standardized. And for steel, the diameter of the ball is 10 millimeters. And for the force, if it's a fairly hard material like steel, it's 3,000 kilograms force, which is about 6,610 pounds. Now, the first problem is that the ball can change shape. So if your ball flexes a little bit and compresses and goes non-spherical, this relationship between diameter of ball and dent changes a little bit. So we have to have a very hard and very stiff ball. So whatever material you're testing, the ball has to be much harder and stiffer than that material. So since I'll be testing some hardened steel, what this is a 10 millimeter tungsten carbide ball. Tungsten carbide is heavier, it's harder, and it's stiffer than steel. So this is kind of the standard. This is, in fact, a 10 millimeter ball. It says 9.99, but that's, I think, acceptable. I think it's a 10 millimeter ball. So we have an appropriate ball. That's the first step. The second step is that we have to measure the diameter of this dent very accurately. We'd like to measure that to the hundredths. Before we get to that, the Brinell hardness is equal to the pressure on this contact surface, and that's measured in kilograms force per millimeter squared. So the second step is how to measure this diameter accurately. So when you do this test, let's see, here's one here. What it does is it makes a pretty obvious dent in my steel. I've colored that so you can see it. We have to measure that with as much accuracy as we can. So what I've been using to do that is this little optical measuring device. I'll show you the insides of this after a bit, but right now, suffice to say is there's some marks. When you look through this, you can see some marks that are 1 millimeter apart, and there's a crosshair that moves with this knob. One rotation of this knob is a millimeter, and it has 100 marks. So this can be directly read to the nearest hundredth of a millimeter, and by interpolating between the marks, you might be able to estimate something in the couple of thousandths of a millimeter. Pretty accurate, I guess. I say I guess because I don't know how to calibrate this. I'm just working with the assumption that it is reasonably accurate on the scale that it's built to work in. Okay, so we have the diameter of the ball fairly accurately provided. We have the diameter of the dent fairly accurately provided. We also have to measure the force with appropriate accuracy. So, we need to measure 6,610 pounds with reasonable accuracy. What I have here is a load cell. This is a 10,000 pound capacity load cell, so it has enough capacity. But it has to be calibrated along with this digital display meter. And if we'd like to end up with a 3 significant figure number, we have to calibrate everything in the system to at least that level of accuracy, a fraction of a percent. 3 significant figures is more accurate than 1%. So we have to be down in half or 1/4% accuracy. So to measure 6,610 pounds with 3 significant figure accuracy, basically I have to be able to measure things to the nearest 10 pounds. And so these two have to be calibrated accurately. You can send them out to be calibrated, but I have an instrument that's made for that. This is called a proving ring. And what happens is you load this up in compression. This ring squishes down, and by closing this gap between the measuring reed and the top of this micrometer, you can measure forces to within a fraction of a pound if you're careful. So this is a 6,000 pound capacity proving ring. What I did is took this and mounted it on top of the load cell, something like that. I loaded this up in my press. The proving ring is only really good at measuring static forces, so I applied a static force to this. Measured that once everything had settled down. I measured that force with the proving ring and simultaneously with the load cell, and by adjusting the calibration of the load cell, I'm pretty confident that I have this calculated to read to the nearest 10 pounds up at least to 6,000 pounds in that range. Okay, let's see what else. So then, once we've measured the diameter of the ball with accuracy, and we've measured the dent with accuracy, and we've measured the force with accuracy, we don't want to just go charging ahead and assume that we've done everything correct. We need to check our work. So what I did is I bought a sample of steel that has been provided with a calibration sheet for a known hardness. This actually is not The known hardness that it's published with is actually a Rockwell C hardness, but that's okay. It gives me some confidence that my results are accurate. I measured the hardness of this using my setup, converted that to Rockwell C, which isn't a precise conversion, but it gives me a ballpark answer. And my testing came up with hardness that was reasonable for the published hardness of this sample. So I feel confident that my system works pretty well. So I'll give you a look at how I set it up and how it works. Okay, so this is the piece I'm going to test. It's a piece of hardened and tempered steel. And the surface we're going to test, I've sanded this flat and polished it up a little bit. You should have a plainer and fairly polished up surface so that the dent is accurate. And here's my load cell. And I'm going to put this on top of a little anvil on the load cell here. The load cell, above the load cell is this hydraulic cylinder, and of course the pump, and that brings down the little, the bolt I have as a loading pin. The bolt has a recess in the end of it that fits the 10mm ball. So I can bring this down here kind of close. I hope I have enough stroke on the ram. I might not. I might have to add a spacer. Let's do that. So I just have all this scrap metal in here to take up enough space to get everything close enough. So let's put this plate on here to spread it out. Put the load cell on top of that. Oops, we're a little close now. Raise up the cylinder a little bit. Okay, there we go. And we'll get this centered up, sort of underneath there. And here's my little 10mm ball. Let's see here, I need 6 hands to do this somehow. There is zero way that that is going to stay in there. Okay, give me a second. Okay, I got the ball in place now, and we can start loading it up. Let me put the display over here someplace. There, how's that? Can you see that? I guess. So we'll bring this down and we'll touch off. I'll bring this up to, we're looking for 6,610 pounds. No hurry here. What we're interested in is accuracy. So 6,000. Oops, overshot a little bit, but that's okay. We're gonna maintain that force for a little while here. It's supposed to be 10 seconds or something like that. But when time's up, we're gonna crack this loose and try to catch my ball, which might stay put. There we go. And look at our display here. and our peak force was 6,688 pounds. So we can take that into account when we do our calculations. Okay, we're going to look at measuring the dent. Okay, you can probably, I wonder if you can see the dent. So we have to measure that dent very accurately. And what we're going to do is set this on top of the dent and look down through it at the picture. But the problem is this slides around pretty easily. So my solution to that is I have some double-sided sticky tape here. I'm going to put a couple pieces of this, one on each side of the dent. Like so. And then we're going to put this into position. Where is the dent? Okay, now that's stuck down pretty well. And we can take our measurements, put some light on it. Let's see if I can give you a look at it. So, if you look through, first off, while I got you here, you can see the dial here. So this is 0, and if you turn this, 0, 10, 50, 100, that's 1 millimeter that the crosshair is going to move inside of there. And so inside you'll see some marks that are 1 millimeter apart. So there you can see the dent. Well, I can't really get that centered up, but suffice to say, when I look through it, I can see much better. So it looks like that side of the dent is about 2 point something, and this side of the dent is going to be 4 point something. So I can position that crosshair very carefully and write down the 2 readings I get, and the difference will be the diameter of my mark. Now you're supposed to do that at least twice, 90 degrees opposite. So I'll take these 2 readings, then I'll lift the scope off, turn it 90 degrees, take 2 more readings, and the average of those 2 is what we'll use in conjunction with the applied load and calculate the pressure on that surface. So let me take care of that. Okay, here's what we've got. So I took 2 measurements of the dent, and the average dent measurement comes out to 2.813 millimeters. Our applied force was equal to 6,688 pounds, which is equal to 3,033 kilograms force is the units we have to use. The Brinell hardness, which should be notated as HBW, is going to be equal to 2 times the force divided by 2 pi times the diameter of the ball minus the square root of the diameter of the ball squared minus the diameter of the dent squared. Okay. When I plug those things in, the Brinell hardness works out to be about 478. The correct units for that are kilograms force per millimeter squared. This, if you look at some comparison charts, again, the conversion is not precise, but this is a Rockwell C hardness of about 52. Trying to think of anything else that's of import. I think that's it. Accuracy is the main problem. For instance, the diameter of my ball, which I seem to have lost, I need to double check that and make sure that that is pretty accurate here. But I can do that on my own time. Accuracy is the main problem with doing Brinell hardness. The accuracy of the ball is fairly easy. If you have 60-some bucks to spend on a optical measuring device, that's not too hard. Like I said, the ball was about 25 bucks. But the hard part is the load cell and its calibration. I think if you bought a calibrated load cell for just this purpose, I think you'd find it's prohibitively expensive. Plus, things don't stay in calibration, so just because it's calibrated today doesn't mean it will be calibrated tomorrow. So you need to have ways to verify these things. Okay.